So after last week covering the mean value theorem, this week what I'd like to do is to take a look at some important applications of it. Now these are not going to be in one sense kind of mind-blowing applications that are going to surprise and shock you or anything like that. They're more going to be things that when you spend a minute thinking about them, you're going to be like, yeah, that kind of seems like what we would expect. And that's fine, right? A lot of times in math, we do kind of just get what answers we expect out of a problem. That can be a good thing, because if you get something you didn't expect, then maybe you did it wrong. Of course, sometimes counterintuitive things can really happen, but in this case, that's not what's happening here. What we're going to see is some fairly intuitively clear stuff, but we're going to use the mean value theorem to make it precise. So what I would like to look at, first of all, is intervals of increase and decrease. So we will say that f of x, a function, is increasing or respectively decreasing on the open interval a up to b if for any pair of values in here, x1 and x2 in a to b, with x1 less than x2, we have f of x1 smaller than f of x2. And in the case of the decreasing, we have f of x1 bigger than f of x2. So I'm writing it this way because I don't feel like writing the same definition twice and just flipping the inequality. So I'm writing out these two different definitions sort of at the same time. Now, this is not really anything particularly new. You probably saw this in your, let's say, your pre-calculus class. I don't know why the word pre-calculus took me forever to think of, but there we go. You may have seen this kind of thing in your pre-calculus class, talking about increasing and decreasing and things like that. But I needed to remind you of this definition because now we're going to use it. Now, here is something that I want to observe. Hopefully you've got that definition down because it's gone. Also, somebody came in and cleaned my board. I'm very pleased about that because it was kind of a mess. I don't know who did that, but thank you to the maintenance people who took care of that, whoever they may be. So what I want to think about now is, what do derivatives tell us about increasing and decreasing? Well, if you think about what is a derivative, right? A derivative is a rate of change. It tells you how something is changing. So we would kind of expect that if you are increasing, or rather, if your derivative is positive, you should be increasing. And if your derivative is negative, you should be decreasing. Because if my rate of change is positive, then I ought to be getting bigger. And if my rate of change is negative, I ought to be getting smaller. And in fact, we can prove that this is precisely the case. There might be other ways of doing it, but the mean value theorem is one that gives it to us almost immediately and without having to think explicitly about limits. So we're going to use that. So let us suppose that if f is differentiable on an open interval a to b, then the following are equivalent. F prime of x being bigger than 0 on the interval from a to b, this is equivalent to saying that f is increasing on a to b. Now, why is this true? Well, one direction is almost immediate, actually, and does involve going back to look at the limits. So showing that if f is increasing and it's differentiable, then the derivative is positive, this is very simple. Actually, it's not very simple, but it's reasonably straightforward. It's not like we need any sort of trickery here. If f is increasing, then the limit as h goes to 0 from the right of f of x plus h minus f of x divided by h. This is a limit of positive numbers, and therefore this is going to have to be, actually, I'm sorry, I should say bigger than or equal to 0. and increasing in the sense that f of x1 is less than or equal to f of x2. Often, this is actually called non-decreasing to emphasize that, well, maybe it's constant for a bit, but it doesn't have to be. So if this is a limit of positive numbers, then the limit is going to have to be positive or 0. So this is going to be bigger than or equal to 0, and the limit as h goes to 0 from the left, f of x plus h minus f of x divided by h. Well, if this is increasing, an increasing function, then the numerator is negative and the denominator is negative. That makes the fraction positive, so that limit is also going to be bigger than or equal to 0. But actually, we just need this one-sided limit because we said this thing is differentiable. So obviously, these limits have to agree, and therefore they have to be bigger than or equal to 0. So if your function is increasing on an interval, then the function has to have a positive or 0 derivative at every point in there. Notice it can have places where the derivative is 0. Look at the function x cubed. X cubed is always increasing on the entire real number line, but it does have a place where the derivative is 0. So there are situations like that. But now comes the part where we're going to use the mean value theorem. We're going to say that if f prime of x is bigger than 0 on the interval from a to b, f is strictly increasing on a to b. Why is this true? Well, here's the reason. Given x1 and x2 in the interval from a to b, remember this symbol just means elements of the set. So these are two numbers that are in the set. With x1 less than x2, we know that f is continuous and differentiable on this entire interval. So f is continuous on the closed interval from x1 up to x2, and it is differentiable on the open interval x1 to x2. Sorry, it takes me a minute to write down all of these technical conditions here. So it satisfies the conditions of the mean value theorem. So by the mean value theorem, which I apparently cannot write MVT, there is a C with x1 less than C less than x2, with f prime of c being equal to f of x2 minus f of x1 divided by x2 minus x1. Now, what can we say about this? Well, x2 minus x1 is a positive number. So this denominator is positive. We can also say f prime of c is positive because we know that f prime of c is bigger than 0. And then we can say, well, that means that this numerator has to be positive as well. Because if this is positive, then this fraction has to be positive. And therefore, this numerator has to be positive. So we can say, really, 0 is less than f prime of c, which is equal to this ratio. But that means that this numerator has to be bigger than 0. And therefore, f is actually bigger at x2 than x1. But we didn't specify x1 or x2. We just said take any 2 points in there. The only condition was that x1 be smaller than x2. So for any 2 points that I pick, f of x2 is bigger than f of x1. Sorry, f of x2 is bigger than f of x1, and that finishes off my proof. It proves that f is actually increasing on a to b. Because remember, what does it mean to be increasing? Well, it means for any pair of numbers, x1 and x2, inside this interval with x1 less than x2, I get f of x2 is bigger than f of x1. And that is exactly what we have found here. So there we go. We have managed to prove this theorem using the mean value theorem. Now again, intuitively, is this any kind of a surprise? No. If the derivative is positive, then we should always be increasing. That's like what we kind of think of the derivative telling us. And so really, the mean value theorem allows us to prove this logically, okay? It gives us the actual detailed proof. But intuitively, this is something that you might have even considered so obvious that you wouldn't even think of trying to prove it in some sense. Now, we mathematicians, we don't take anything for granted. We always say it may be obvious, but we still want to prove it because sometimes things that are obvious in math turn out to be not quite right, or even sometimes totally false, okay? So that's why we're so careful about these sorts of things. But yeah, this is not like a surprising result in any kind of way. And we can go the other direction as well. So we can say that if the derivative is less than 0 on a to b, then f is decreasing on a to b. I'm not going to do the proof of this one again because it's literally the same proof a second time. Oh, give me 1 second. Okay, so what we want to do now is to take a look at how this helps us understand the behavior of functions. Well, in one sense, it's kind of obvious, right? It tells us that if we look at a differentiable function, we can see where it is increasing and where it is decreasing, right? Now, the interesting thing is that that is actually going to give us a little more information than just where this thing is increasing and where this thing is decreasing. But first of all, let me just show you, how do you find these intervals where something is increasing and decreasing? By using this method. So I want to start with one that's reasonably straightforward. As usual, this is going to be one where we really don't even need calculus for it necessarily. So let's suppose that I want to find the intervals of increase and decrease for f of x is equal to, let's say, 2x squared minus, let's say, 6x plus 1. Well, here's how we're going to do it. One way we could do this, of course, is we could say, hey, this is a parabola. I'm going to find the vertex algebraically, and then that tells me I look and see this is an opening upwards parabola, so it's going to decrease until we hit the vertex, and then it's going to increase. But I want to show you how to do this with calculus. I would take the derivative, and I would say f prime of x is equal to 4x minus 6. Therefore, the critical point is going to be 4x minus 6 equals 0. That gives me x equals 3/2. And now, what I can do is I can say, here's my 3/2 critical point. The derivative is a continuous function, and therefore it only changes sign at its zeros. In other words, the only way that a derivative can change signs is at a critical point, because either it has to go through 0, which is a critical point, or it has to be a discontinuity, in which case it could jump around and do whatever. But either way, it's a critical point. So all I have to do now is check, is the derivative positive or negative on either side of this? Well, if I plug in, let's say, 0 as a test point, I would get 4 times 0 minus 6, that's negative 6. So f prime is less than 0 here. That means we are decreasing. And if I plug in, let's say, 2 as my other test point, I get 4 times 2, that's 8, minus 6, which is positive 2. Why is the camera having so many issues today? Let's hope that fixes things a little bit. And that means f prime is bigger than 0 over here. Well, this means by our previous result that the function, not the derivative, the function, is going to be increasing on the interval from 3/2 up to infinity, and it's going to be decreasing on the interval from minus infinity up to 3/2. So there we go. We have figured out now where this thing is increasing and where this thing is decreasing. Now, one thing I'm going to mention here, something that can help you out as well. Look at this critical point, okay? If this critical point goes from decreasing to increasing, then that means that this critical point actually has to be a minimum. Because if I go from if it's differentiable at this point, we got to be careful if there's a discontinuity, because if there's a discontinuity, some weird stuff can happen. But if the function is differentiable and it has a critical point where the derivative is 0 and it goes from decreasing to increasing, then what has to really be going on is we're decreasing, we hit a place with a horizontal tangent, and then we go to increasing. Therefore, this has to be a minimum because it has a place where the derivative is 0, and on one side it's decreasing, and on the other side it's increasing. To prove this precisely, go in and use the limit definition of the derivative. You'll see that the right-hand limit is going to have to be bigger than or equal to 0, whereas the left-hand limit has to be less than or equal to 0. So the only option is that it's equal to 0. Now, if the function is not differentiable at this point, then all bets are off, because in that case, we could have something happen like this. I could come in like so, and then jump upwards and go like this. This goes from decreasing to increasing, but this is not technically a minimum. Sorry, let me make sure you can see that. This is not technically a minimum because of the way the function is jumping around. So we do need to say this only works if the function has a well-defined derivative that becomes 0 at this point. But if that happens, then this automatically tells us for free that this is a minimum. And you can see that the same thing is going to happen if we were to go from increasing to decreasing, right? If I go from increasing to decreasing and it's differentiable, then the derivative is 0 at this point, and it was increasing, and now it's turned around and it's decreasing. So it would be the same picture, just flipped upside down. And therefore, we would know that this is a maximum. So if we're looking for minimums and maximums of our function, local minimums and maximums, that is to say, one way to decide which is which, we talked last week about how you can do it kind of directly. You evaluate the function at the critical point and you evaluate on either side of it and you see what happens. Well, the problem is that that's kind of a lot of work in a lot of cases. It might be rather tricky to do as well, especially if your critical point is something annoying. Like maybe your critical point involves some irrational square roots or something like that. Well, in that case, what you might be able to do more easily is just look at the derivative and look at where is the derivative positive and where is the derivative negative. So let's take a look at another example of this kind of problem and see what we can do with it. And then see what that also tells us about the critical points. So we're going to start by finding the intervals of increase and decrease. Then we're going to find the classify the critical points as maximums or minimums. So let's take a look at, let's suppose that I have something like negative 3x cubed plus 9x squared minus 15x plus 2. Well, what I'm going to do is I'm going to look at the derivative here. The derivative is going to be minus 9x squared plus 18x minus 15. Oh God, did I accidentally set one up that's going to not do what I want to do? Well, let's see what happens, because maybe we're going to find that there are no critical points. But no, we should be okay here. So if I try to solve this thing, I set negative 9x squared plus 18x minus 15 equal to 0. This is the same as if I divide everything by 3, we're going to get negative 3x squared plus 6x minus 5 is equal to 0. Oh crap, I did write one down that has no critical points. If you try to solve this thing, b squared minus 4ac, that's going to be 36 minus 60. So this actually has no critical points. Well, that's okay. Let's see what happens when you have no critical points. This is what happens when I write down an example and just make it up off the top of my head. But if you have no critical points, well, that means that we are either always increasing or always decreasing. Well, which one is it? I can look at this derivative and I see that if I plug in x equals 0, the derivative is negative. So we see that f prime of x here is always going to be less than 0. So f is decreasing on the entire real number line, like so. By the way, another way of writing the entire real number line is like this. It's called a Blackboard R. It looks just like a regular R, except the left-hand side has been thickened up with an extra line. And this Blackboard R is a standard symbol for the set of real numbers. So I accidentally wrote down an example that in some sense isn't all that interesting because it's just always decreasing, but I'm kind of glad I wrote it down because it shows you what to do in these kinds of situations. And now we won't have to make up an example like that to demonstrate it. Okay, so let's move back for a moment and see what would happen if we made this into a problem that does have some critical points. So let's suppose that instead of the original problem, what if I just make that first term into a negative x cubed instead of a negative 3x cubed? I think that will fix what we just had to come up, but I'm not 100% sure. We'll see. So this time we're going to have f prime of x is equal to, actually, you know what? Just to make sure this thing works for us, we are going to make this into a negative 9x instead of an 18 or 15, whatever that number was. Why am I so confused about what that number was? Anyway, that's now going to be a negative 9x. So when I take the derivative, this is negative 3x squared plus 18x minus 9. I take that and I set it equal to 0. And when I set that equal to 0, I can divide everything through by 3. That gives me negative x squared plus 6x minus 3 is equal to 0. Now, if I set this thing equal to, if I use the quadratic formula here, I should say, this is going to give me negative 6 plus or minus square root 36 minus 4 times minus 3 times minus 1. I don't know why I wrote it in that order. We'll put the a first as usual. Minus 1 and minus 3. And then on the bottom, we've got 2 times minus 1. So this is going to give me negative 6 plus or minus square root of, let's see, 4 times 3 is 12. So this is 36 minus 12, which is 24. And on the bottom, we have a negative 2. So this is 6 plus or minus 2 square root 6 divided by 2. Notice that I multiply the numerator and the denominator by negative 1. But when you do that, the plus or minus stays a plus or minus, because if you multiply plus or minus by negative 1, it just stays a plus or minus. And this is then going to become 3 plus or minus the square root of 6. So there we go. These are going to be our critical points. Now it remains to be seen what happens at these critical points and where the intervals of increase and decrease are. But for the moment, let's just set aside that these are our critical points and take a moment to make sure you have this written down because I have to erase it. And now what we can do is on our number line, we are going to put our 2 critical points. So we have 3 minus square root 6 and we have 3 plus square root 6. Now, why did I erase the derivative? I actually need the derivative still. So that's going to be negative 3x squared plus 18x minus 9. Okay, so a few things that we can say. 0 is going to be to the left of 3 minus square root 6 because the square root of 6 is smaller than 3. So 0 works as a test point, and f prime at 0 would be negative 9, which is less than 0. In the middle here would be 3. I know that 3 is going to show up in there, but actually another test point I could use is positive 1. Maybe positive 1 is even easier. Why do I know that positive 1 sits in here as a test point? Well, because the square root of 6 is bigger than 2. So 3 minus the square root of 6 is smaller than 1. If I plug in 1, I would get negative 3 plus 18, that's 15, minus 9 is positive 6, so we get f prime bigger than 0 in here. And our last test point, we can say, well, anything bigger than 3 is, anything bigger than 6 will work. So you can plug in, let's say, 7. Actually, we don't even need that much, do we? Because square root of 6, yeah, we can just plug in 6, because 3 plus square root of 6 is 3 plus a number that is smaller than 3, so it is smaller than 6. And if I evaluate the derivative here, I get f prime is less than 0 again. I'll leave it to you to do the details. Although actually, in this case, we don't even need to bother with the test points. The reason is because this is a parabola that is opening downwards, and it has 2 zeros. Therefore, we know the derivative is positive in between its zeros and negative on the ends. So what this means is that our original function is going to be decreasing on minus infinity up to 3 minus square root 6 and 3 plus square root 6 up to infinity. It's going to be increasing on 3 minus square root 6 to 3 plus square root 6. And then, what are these critical points? Well, if I go from decreasing to increasing, this is going to have to be a minimum. And then I go from increasing to decreasing, so this is going to have to be a maximum. So what is the shape of this graph going to look like? Well, the overall shape is not too difficult to draw in here. Actually, I'm not going to put the axes because I don't want to worry about the intercepts. But the overall shape is we are decreasing. We come to a minimum, we come back up to a maximum, and then we go back to decreasing. Now, if you want to know precisely where this minimum and maximum happens, you can go ahead and plug those numbers into the original function. You may even just want to get a decimal approximation or whatever, but you can do that kind of thing. So this is sort of the utility of using the derivative. It tells us where the function is increasing and where the function is decreasing and things like that. So I'd like to give you a problem like this and ask you to take a couple of minutes to think about it now. So let's suppose that you want to find the intervals of increase and decrease for f of x equals x cubed plus 6x squared minus, let's say, 9x minus 2. And also classify the critical points as maximums or minimums. So pause this for a minute and see what you can do. All right, were you able to get anything? So let's start by taking the derivative. That's going to give me f prime of x is equal to 3x squared plus 12x minus 9. When I set this equal to 0, we're going to have 3x squared plus 12x minus 9 equals 0. That becomes x squared plus 4x minus 3 equals 0. And I think this factors, does it not? No, it does not factor, because we would need them to multiply to negative 3, but add to 4. So we're going to use the quadratic formula here and say x is going to be 4 squared plus or minus the square root of 16 minus 4 times 1 times negative 3 divided by 2 times 1. So that gives me x is equal to 16 plus or minus the square root of 16 plus 12 is 28 divided by 2. This becomes 16 plus or minus 2 square root 7 divided by 2, which is 8 plus or minus the square root of 7. So there's my critical points. So now all I have to do is figure out where is this thing increasing and where is this thing decreasing. And to do that, I just need to look at where is this derivative going to be positive and where is this derivative going to be negative. So let me erase the part where we solve for the critical points just so I have a bit more space. And I will make a number line with my critical points. So that's going to be 8 minus square root 7, 8 plus square root 7. Now, we could go ahead and we could use test points. But once again, I could also just argue that, look, this derivative is a parabola. It opens upwards. Therefore, it has to be negative in the middle, and it has to be positive on the ends. Because that's what parabolas do. They cross the axis twice, or they don't cross it at all, and that's it. So in this case, what we can say is the original function is going to be increasing on minus infinity up to 8 minus square root 7, unioned with 8 plus square root 7 up to infinity, and it's going to be decreasing on 8 minus square root of 7 up to 8 plus square root 7. And it's going to have a maximum here at 8 minus square root 7, a minimum at 8 plus square root 7. So there we go. We've been able to find the intervals of increase and decrease using the derivative and then use that to figure out whether this is a maximum or a minimum at each of these critical points. Now, this test for maximum or minimum, this is also called the first derivative test. So, if your function is differentiable at a critical point, in fact, let's write this down carefully. If f prime of c equals 0, then f changes from minus to plus. This means that f prime changes from minus to plus. C is a minimum for f. And if f prime changes from plus to minus, then C is a maximum for f, a local minimum and a local maximum. So this is what is known as the first derivative test. And you'll notice the nice thing about this is we don't need to do as much evaluation as we do to just directly see whether a critical point is a minimum or a maximum. Because normally, if we just plug in some values, we need to plug in at least 3 different values. And then what we have to do is, well, that evaluation might be tricky. And then we've got to compare them. So we usually need to evaluate them all precisely to see which one is the biggest and which one is the smallest and all that kind of thing. The first derivative test, we don't need to do any of that. We just need to decide, does this thing change signs? Does the derivative change signs? And if it changes signs, that gives us our answer right away. So the first derivative test is really a lot more convenient than just directly looking at the critical point. However, I do want to say that you can go in the other direction. So a lot of the things that we're going to be studying here in chapter 4, there's all kinds of relationships that go in both directions. And in this case, what's going in both directions is that if I know, for whatever reason, that this is a maximum, then I know that my function has to change from increasing to decreasing. And if I know that this is a minimum, then I know that I have to change from decreasing to increasing. So if for some reason you already classified the critical points, then that tells you something about where your function is increasing and decreasing as well. And that can be a very useful fact, because occasionally it might be, for some reason, advantageous to classify the critical point first and then look at the intervals of increase and decrease. However, I would say that normally we want to find the intervals of increase and decrease first, and then we can use something like the first derivative test in order to find where this thing is increasing and where this thing is decreasing. Now, we're going to look at more examples of this kind of thing, but I think this lecture has gone on long enough for now. So I'd like to kind of stop here and give you some time to think about this, try maybe a few more examples on your own, look at the book. Now, what we're going to want to look at next time is I do want to take a look at what happens if, let's say, we are dealing with a rational function. I just did a bunch of polynomials, but we might be dealing with a rational function where there's places where the function itself is undefined and where the derivative is undefined. All kinds of weird stuff can happen in those cases. So it's not actually too bad. It's really just kind of, you got to treat those points differently, and anything can happen on either side of them. So you break up your interval, first of all, into the different intervals comprising the domain of your function, and then you do this analysis on each one of those intervals. So it's not really like it's that bad, but it is something that I think it's worth taking some time to go over, and I'd like to come to it fresh in a new video rather than just tacking it on to the end of this one. So we're going to end this here for now, and let me know if you have any questions. I will be putting up another video soon.